the shorter and shorter their wavelengths are. Their frequency gets higher and higher. When they started talking about light, they had some good formulas, but they didn't have enough to explain black body radiation and the photoelectric effect. And I'll get into what the photoelectric effect is in just a second or two. All right, so Max Planck proposed an idea for electromagnetic radiation being emitted just in little bitty amounts, little bitty bits, which was very different than what they had thought of before. So for instance, what it's saying is that you're giving off certain amounts of light, and how that happens is, let's say we have a nucleus here. I'll just put N for nucleus. Well, I'll put P and N. That way you know protons and neutrons there. All right, so then the electrons are outside of it. And so we have all of these different energy levels, and as you get further and further from the nucleus, they get closer together. So this is N equals 1, N equals 2, I'm trying to write with mouse today, N equals 3, 4, and 5, and so forth. So let's say we have an electron here. What it's saying is when light comes in and hits this electron, it can absorb energy and jump up to the next level, or it could jump up to level 3 or 4 or 5, depending on what the frequency is of the light that hits it. But what's not going to happen is the electron is not going to start out here and end up here. It's going to go only in specific places. And they explain it kind of like stairs in the textbook, which was actually a pretty good explanation, because when you're on a step, let's say you were on this step here, and you go to step on the next step, you'd step on this one. You wouldn't just be floating in midair here, kind of waiting to go to the next step. Although that would be a really cool set of steps. But and that's kind of the idea of quantum physics. Quantum physics, quanta just means like a quantity, an amount. And so Max Planck got this idea of photons, which are little packets of light that will be emitted depending on where the electron is. And as we go through this, it'll become a little bit more clear, because the ideas are kind of out there when it comes to quantum. So the first formula they give us was this one, E equals H nu. And this nu, this little V-looking thing, is the same one we had before, where we had nu equals C over lambda in the last section that we went over. So the nu there is frequency. So this is the frequency of light. E stands for the energy of a photon, and H is Planck's constant. So Planck's constant is always the same. You will need to memorize Planck's constant. So if you look at nu is equal to C, which is the speed of light, over lambda, which is the wavelength. So there are two ways they can word this question. Well, three. They could say, if the energy of a photon is, and they give you some number, what is the frequency? Or what is the wavelength? But they'll give you one thing, and they'll ask you to calculate the other one. They could give you the energy, they could give you the frequency, or they could give you the wavelength. Any of those. And I think there's an example on here that I worked out later on in the notes. A photon is just a quantum of energy, or a packet of energy, most often is referred to as a packet of light, which sounds crazy because we've talked about it being a wave, and now they're saying instead of being a wave, it's like a particle. It's an individual thing. Instead of being like a wave of stuff, it's just an individual thing. But really it's both, which is what they call the wave-particle duality, which would have been really good to introduce in these sections, which the book didn't. All right, so here is an example that's in the textbook. It's asking, what's the energy of 1 mole of photons? The problem is they didn't introduce, well, they probably introduced a mole in sections 2.4 and 2.5 and so forth, but we haven't done those yet. So it makes this problem even more challenging. So I'm going to tell you what a mole is to make that not challenging. If you have a dozen eggs, how many eggs do you have?
More than 2. Or 2 or more.
12. Right.
Oh.
Okay. So if you have a dozen is a number of things, and it's 12. And a gross, I think, I'm not sure on the gross, but I think a gross is like 144 things. So a mole is the same kind of idea, it's just a lot more stuff. So it's 6.022 times 10 to the 23rd things.
Oh.
So it would be 6022 and then 20 more zeros. And that's 12. How many things 1 mole is. They make it that big because we're talking about electrons and atoms and things like that, and they're itty bitty. So even to get like a speck of them, you have to have a lot. So they use the mole instead of like a dozen instead. So they gave you the wavelength in this problem, and they gave it to you in nanometers. Now, there are a couple things to note here. One is that it's asking for the energy of a mole of photons. Let's see. Yes, the mole is a constant. It's called Avogadro's number. And you've probably heard of Avogadro's number before.
Yeah.
So it's 6.022 times 10 to the 23rd. So one of the formulas is E equals H nu, but since nu is C over lambda, that's all they've done here is they've substituted in C over lambda for nu. So E equals H C over lambda. C is the speed of light. H is Planck's constant. E is the energy of 1 photon. And that's really important to know because the question's asking for a mole, but before we can find a mole, we need to find the energy of 1, so then we can multiply it by Avogadro's number. So below that, I've put in the information. So I've put in Planck's constant, and the units are joule seconds. Joule is a unit of energy. And then next to that is the speed of light in meters per second. If you look at the wavelength they gave it to you in nanometers, so that has to be converted. So 1 nanometer is equal to 10 to the negative 9 meters. So at the top of the page, I just converted that to meters. So once I converted it to meters, I put it on the bottom of the equation here. And if you notice, if you're paying attention to the units, the seconds will cancel out. And I multiplied the top 2 things. And then the next part of the equation is where I've multiplied the top 2 things, Planck's constant and the speed of light. And then the seconds canceled, so the units are now joule meters. And then the wavelength is on the bottom, meters cancel, it's going to give you units of joules. And that's one way that I know that I'm on the right track, because energy is in units of joules. So 1 photon, when you do the math, and it's very important when you're doing these problems to use parentheses in your calculator, because you can do the entire problem correctly and mess up the parentheses, and the entire problem ends up wrong. So make sure you're using parentheses correctly. So 1 photon is 3.10, et cetera, times 10 to the negative 19th joules. I think I heard a comment. That's a good question. Let me show you how they cancel. Joule seconds, okay. I'm gonna do it on the whiteboard. Okay. So we have Planck's constant, which is in joules seconds. And then we have the speed of light, which is in meters per second. And then we have the wavelength, which is in meters. So with the seconds, we actually have one on top and one on bottom. So that leaves us joule meters divided by meters. The meters cancel, leaving it in joules. All right. So let me share the notes again. All right. So at that point, I have one photon, but I'm not done because it wants a mole of photons. So when you work these problems, it's a conversion problem. We know that 1 mole is equal to 6.022 times 10 to the 23rd things, and in this case, the things are photons. So 1 mole of photons is the number you start out with. Let's say they had said how many are in 6.7 moles of photons. Then instead of 1, you would put 6.7. So in this case, they just want to know 1 mole of photons. So you start with 1 mole of photons, and then you use the unit conversion. 1 mole of photons is 6.022 times 10 to the 23rd photons. Moles cancel. And then from the problem we just solved right above it, we know what 1 photon equals in energy. So that's our next conversion. So it's 1 photon is 3.103, etc., times 10 to the negative 19th joules. So the moles cancel, the photons cancel, and it leaves us in joules. And again, it's really, really important to use your parentheses. And then the calculator spits out this really long number, 186,914, etc. And then when paying attention to significant figures, you end up with 1.87 times 10 to the 5th joules per mole of photons. Let's see. Yes, they are. And let me show you how you figure those out. All right, so when you look at the information the problem gave you, 640 nanometers. So that was 3 significant, well, I'm assuming they meant 640.0 is what I would normally have expected, but since I didn't put a decimal there, you really only know of 2 significant figures. So it'd be like 6.4, or not 6.4. It'll be 6 and the 4, but the 0 doesn't count because there's no decimal there. So that's 2 significant figures in the wavelength. Avogadro's number is an exact number. The mole is an exact number. So we're really just dealing with 2 significant figures. So when you get through at the very end of the problem, you don't round anything till the end, but at the end, you're going to round it to 2 significant figures. I actually did it to 3 here because I wasn't paying attention to the fact they didn't have a decimal. But if they had put a decimal, then it would have been 3 significant figures. And it would have been 1.87. So significant figures do count. A lot of times with these problems, they're not going to give you answers that are super close, like 1.87 or 1.875 times 10 to the 5th, because they're more interested in whether or not you can work the problem than whether or not you can calculate the significant figures. It doesn't mean you don't ever have to pay attention. It just means, in general, they're more interested in can you work the problem. And also, in these kind of problems, the only thing you're interested in is how many significant figures did they give you in the first thing. 10 to the 5th. Okay, that's a good question. Let's see. 10 to the 5th. Not sure what you mean 10 to the 5th. Hang on. Oh, okay. So if you look at the number, it's 186,914, and then the decimal place. So in order to put it in scientific notation, I have to move it 5 places to the left. So move past the 4, past the 1, past the 9, past the 6, and past the 8. And that's 5 places. So it's 1.87 times 10 to the 5th joules per mole. And in this case, we would round to 1.9 if we were going to 2 significant figures, because 6 is greater than 5. So then we would round up.
Mm-hmm.
You're welcome. All right. And then it starts talking about the photoelectric effect. And for that, I want to kind of draw you a picture and kind of explain it a little bit more. So let's say we have some metal. So we have this. Imagine you're in your kitchen and you've laid out some aluminum foil, but then all of a sudden the lights go out. And for some reason, I don't know what reason, and you have to make up some reason in your mind why you would want to do this, but let's say you have no lights, but you have to look at the aluminum foil. So you get a flashlight, and this is going to be the worst picture of a flashlight known to man, so my apologies. And you take the flashlight, and you aim it at the metal. And all of a sudden, you start noticing these things flying off the metal like crazy. That would be really weird. You wouldn't expect that. You wouldn't expect the light to act kind of like a lightsaber and, you know, be causing things to go flying if you're just looking at your aluminum foil. And there are a couple of reasons that that doesn't happen. But the idea of the photoelectric effect is this idea that when you shine light on metal, it can cause electrons to leave the metal. It doesn't always, but it can. And I'll explain that. Wait, no, we've got a couple more minutes. I just looked at the time. I was like, no, I have more to say. Of course, you guys know I always have more to say. It's almost like I will never be quiet. Okay, so they give you the definition of the photoelectric effect. It's electrons ejected from metal when light of sufficient energy is shined on it. That's the main part. It's got to be sufficient energy. And it has to have a certain frequency in order to cause the electron to go up. And then there can be extra energy, and it goes into the kinetic energy of the electron. So let's go back to our idea of the atom. So we have our nucleus. And then these formulas they're giving you later, well, I'll get to that part when I get to it. All right, so let's say we have an electron here in the n equals 1 level. For hydrogen, that's the ground state. Ground state just means the lowest state the electrons can be. So as close to the nucleus as they're allowed to be. Each one of these lines can hold 2 electrons and no more. So if we shine light of a certain frequency and it hits the electron, but this frequency isn't enough to get it to go all the way to at least 1 more level. If it was only going to get it to go here, it's not going to do anything. The light would just kind of shine and then go away. The light would bounce off, no electrons going anywhere. But if you have light of another frequency and the light hits the metal, it's going to the electron is going to absorb that energy of that particular frequency and move up. But it's going to have to move up a whole level. What do you guys think happens when there's not exactly enough for it to go up to the next level, but instead there's more than enough to go up to the next level? So there would be extra energy, and the extra energy goes into how fast the electron is moving? Yeah, that's a good question. So in the photoelectric effect, what we've got is we've got light of a certain energy hitting our aluminum foil, causing the electron to be not just going up to the next level, but out of, not associated with the nucleus at all anymore. So it's just gone out on its own, and it's at n equals infinity. That just means it's not associated with the atom anymore. And so when that happens, it causes the electron to be ejected, and the speed of the electron depends on any extra energy. You can kind of think of the photoelectric effect in terms of going to the gas station and buying a soda. So if you go to the gas station and you buy a soda at the gas station, and it is $1.75, if you give them $1, you're not likely to get the soda. They'll give you the $1 back, and the soda stays at the store. So it's not, the soda never gets ejected from the store, right? But if you give them $1.75, you do get the soda. And you can give them more than $1.75, and you still get the soda. But in the case of the electron, the change that you would get back, the 25 cents the man at the gas station gives you, would be spent in causing the soda to fly really fast out of the gas station. And the more change he gives you back, the faster the soda shoots out the door. And just change soda to electron. So the more energy there is, the faster the electron goes. Does that make any sense at all? It's probably on the verge of no. Okay, a little bit. All right, that's good. All right, so let's head back to the notes real quick. I know we're running out of time. Okay, so the extra energy goes into the kinetic energy of the ejected electron. So Ke is kinetic energy of the electron. And then they give you this whole equation here. Left, it's what's called the work function. That's the energy it takes to get rid of the electron, to move the electron away. H is still Planck's constant, nu is still frequency, and Ke is still kinetic energy. And then they also give you the formula down below it. It's the work function is on the left, that's a circle with the line in it, equals Planck's constant times the minimum frequency. And it gives you a sample problem in the book, which I think isn't a very good problem, but it gives you the minimum energy required to move the electron. So that takes the place of the circle with the line through it. Planck's constant is the same, and then the frequency is what you're looking for. So if you look at this part, this is where I worked it out. On the left is the work function, or the minimum energy required to move the electron, to eject the electron, I should say. And then 6.626 times 10 to the negative 34 joule seconds is Planck's constant. And then nu 0 is the minimum frequency. So if you divide both sides by Planck's constant cancels on the right. And then when you divide those numbers, the minimum frequency is 1.09 times 10 to the 1, to the 15 inverse seconds, or hertz. 3.4 was a little bit more manageable, but not much. They didn't tell you what n equaled, but this n has to do with that picture I keep drawing where there's a nucleus and then I keep drawing lines above it. N just means it's the energy level. The Balmer equation is used to calculate the first lines in the spectrum of hydrogen. And so they have a very specific equation for this, and it's at the top. One thing to remember in this particular equation, and only this equation, n is always equal to 2. M is a number they'll give you. They'll either give you M or they'll give you wavelength and ask you to calculate M. I would assume with the complexity of the equation, they're going to give you M and ask you to calculate the wavelength and not do it backwards like that. Yes, they're on D2L now, actually. All right, M depends on how far away the electron goes. Then they have another equation similar to it called the Rydberg equation. The Rydberg constant is 1.096776 times 10 to the 7th inverse meters. It's important to note this is the Rydberg constant. Frequently, you'll see them give you a different number for the Rydberg constant by accident in YouTube videos, so just make sure that you know that this is the Rydberg constant. Let's see. All right. And then we have NF and NI. NF is N final, and NI is N initial. So what this is 1 over the wavelength equals the Rydberg equation times 1 over the n level where the electron ended up minus 1 over the n level where the electron started. I have a similar equation to that here. The energy of a photon. Bohr came up with this formula. There are a lot of different formulas. There's the Rydberg equation, there's the Bohr equation, and they all pretty much get you to the same place, the energy of a photon. So this is the other equation. Negative 2.178 times 10 to the negative 18 is what they accidentally give for the Rydberg equation on occasion. Not the Rydberg equation, the Rydberg constant, but that's not the name of this constant. I don't know the name of the constant, but it's not the Rydberg constant. Again, N final squared and N initial squared. So let me show you kind of what it's talking about in that equation. All right, so you have the nucleus and you have your N levels. All right, so you have an electron, it goes from N equals 1 to N equals 2. So then you would have negative 2.18 times 10 to the negative 18 times 1 over N final. N final was where the electron ended up. Electron ended up in N equals 2. So that would be 1 over 2 squared. So negative 2.18 times 10 to the negative 18 times 1 over 4. And then the other one is 1 over 1 squared, or 1 over 1. It says, which formulas do we need to know for future tests? There are so many for this chapter. Yes. I am going to take a look at what I'm going to be doing on the test and let you know which formulas are most important. Definitely, and class is over in case you need to go to your next class. All right, let me switch over to the notes and I'll kind of give you an idea of some of those. But if you have to leave, don't worry, because I'll point these out again. This isn't going to be the only time I say these equations. All right.
Excuse me?
Yes.
At the since we have if you have any extra time, can we look over the 3.4 homework problems?
Well, I've got a class that starts in just a couple of minutes. Do you have time this afternoon at about 1 o'clock, 1:20?
1:20. Yes.
Okay, well, I have office hours at 1:20. If you stop by, then I can go over some of your homework problems with you.
Oh, that'd be lovely. Thank you.
You're welcome.
Do I email you or?
No. What you do is you go to D2L, click on content, scroll down to where it says virtual office hours, and then you open the link. Just make sure that you have Zoom downloaded to your computer before you try to log on, because otherwise it gives you some notification like error notice or something.
All
So
right.
just download Zoom and then click on the link and you're good to go.
All right. Thank you.
You're welcome.
Professor, do I need to send the email?